Dear students, welcome back to our online certification course on analog electronic circuits. Myself Pradeep Mandal from E&EC department of IIT Kharagpur. Today's topic of discussion is usage of current mirror. So, we have started the current mirror circuit and today we will be talking about its application. So, according to our overall plan, we are in week 9. In fact, this is course module 8. We have talked about current mirror, its operating principle and analysis in the previous lecture. Today, we are going to discuss more detail of the current mirror, specifically its application. And we do have different applications for this current mirror. One is in common emitter and common source amplifier based on whether it is BJT or MOSFET based implementation. Likewise, in common collector and common drain and common base and common gate, and also in differential amplifier. So, in this lecture, in fact, we can also see the usage of current mirror in signal mirroring, particularly within the differential amplifier. We will be talking about its application as current mirroring circuit. So, what are the concepts we are planning to cover, or what are the subtopic we are going to cover today is the following. To understand or to appreciate the effect of current mirror in amplifier, standard amplifier, where we normally talk about the linearized circuit, whether it is common emitter, common source or common collector or common drain, or for that matter even for differential amplifier. We need to understand the small signal model of current mirror, and to go into the small signal model, we do have two possible situation. One is the current mirror may not be carrying any signal, namely under DC condition, what is the small signal equivalent circuit, and then we do have the second possible situation where the current mirror may carry signal in the form of current. And we will be talking about both BJT and MOSFET version of the small signal model. So, let me talk about the small signal model of current mirror implemented by MOSFET. So, here we do have the current mirror circuit. We do have transistor 1, it is diode connected, and we do have reference current, DC current, that is getting mirrored into this branch through this transistor 2, and here we do have the application circuit. So, we do have the application circuit which is connected to the power supply, and the current flow here, as we have discussed that this current flow here, it is defined by whatever the current we do have here. Now, if you want to have say small signal model of this entire circuit along with the application circuit, we need to know what will be the small signal model of the current mirror. So, here we do have the small signal model for transistor 1. It is having GM1 multiplied by VGS1, that is the current flow, voltage dependent current flow, and VGS it is here. So, that means whatever the voltage we do have here, it is the VGS1, and then we do have from drain to ground, we do have the resistance. Earlier we used to call this is RDS, RDS1. For fair comparison with BJT version, here we are instead of writing RDS1, here we are writing RO1. So, I should say this is a synonymous situation. So, let us stick to this notation. So, we do have voltage here which is VDS as well as VGS. So, we can say that this is the voltage. Now, for small signal model, this is DC current. So, obviously, we have to make the current here, it is since it is 0. So, we can say it is this circuit is open. So, we do have open circuit here, and then if this portion it is open, then if we have the small signal equivalent circuit, what we can see here, the solution of this voltage VGS voltage, it should be 0. That is because if I consider say this loop, and this is having a solution only when the VGS1 equals to 0, and mainly because this side as well as this side they are connected to ground. So, that makes the VGS1 equals to 0, and incidentally VGS1 and VGS2 they are equal. So, that makes VGS2 also equal to 0. On the other hand, the small signal model for transistor 2 M2, we do have GM2 multiplied by VGS2, and VGS2 as I said that it is same as VGS1, and also it is having drain to source resistance, either we call this is RDS2, or in this discussion we are calling this is say RO2. And then we do have the application circuit. So, now this is the actual application circuit, and here this is the small signal equivalent circuit of the application circuit. So, this is small signal equivalent circuit of the application module. And then whatever the voltage we do have this voltage. Now, since VGS2 it is equal to 0, so we can say this part it is equal to 0. So, as a result what we have it is small signal model, we do have only this part left behind, which means that if we do have this reference current is having only DC component, and then suppose in the application circuit we do have some analog signal coming, and then probably we like to know what will be its corresponding transfer function. Then to get the linearized circuit of the entire portion, we need to draw this small signal circuit here, and out of this entire current mirror what you will be having it is only RO2 left behind. So, I should say the small signal equivalent circuit, whenever we do have a current mirror, then it will be very simple. We do have the small signal equivalent circuit of the small signal equivalent circuit equivalent of application, and then we do have simply this resistance RO2, and then of course, in this node it is connected to AC ground. Okay. So, likewise whenever we do have a current mirror getting implemented by BJT instead of MOS, then also we will be getting similar kind of circuit. So, let us see that. So, here we do have the current mirror, and again we do have a reference current is only DC. Here we do have the application circuit, or application module, and we like to draw the small signal equivalent circuit here. So, this is the VCC, and to draw the small signal equivalent circuit, what we have for transistor 1, we do have RO1 from its collector to emitter. So, this is the, I should say, collector node as well as the base node, and base node, as base node and collector nodes, they are connected together. And then we do have GM into VBE1, and what is the VBE1? This is the voltage. We do have the VBE1. This should be VBE1. Okay. And we do have, of course, R pi, unlike MOSFET. Here we do have R pi 1, and then we do have R pi 2. So, these two resistors, they are coming in parallel, and then whatever the voltage you do have here, it is VB1. In fact, the voltage across this VB1, it is the voltage here, and that VB1 incidentally it is same as VB2, or rather VB2 it is equal to VB1. And again, since it is a DC current, for small signal equivalent circuit, this is open, and in this network, particularly in this network, if you see, here we do have ground connection, here also we do have the ground connection, and the only solution for this VBE is equal to 0. So, that makes VBE2 also equal to 0. So, this current flow here, voltage dependent current flow, it is GM into VBE2, and since this is 0, this part it is also becoming 0. And here we do have the small signal equivalent circuit of the application module. Equivalent circuit of the application module. And so, now whenever we are feeding signal to this application circuit and we like to know what is its corresponding transfer function, then this portion, entire portion, we can completely omit. We can just consider this RO2. As a result, the corresponding small signal equivalent circuit, it becomes like this. So, this is the small signal equivalent circuit of the application module, and then only RO2 it is there. So, that is how we consider the small signal equivalent circuit for a situation where the current mirror, it is not carrying any signal current, or rather whenever the reference current is DC. Situation when may arise when this reference current may have a signal part, namely say I in, and in that case obviously this will not be 0, and this may carry some signal to this voltage dependent current source. So, let us see that situation. So, in the next slide we do have this situation. Yes, here we do have the basic current mirror, and now the difference here it is, along with the DC reference current, it is also having signal current I in. So, this signal current, it is again it is coming from either DCU or whatever it is, but finally at the drain node of the MOSFET it is arriving, and it may be producing a voltage here. So, this VGS 1 is now it is function of I in and it is non-zero. So, here we do have the small signal equivalent circuit drawn here. For transistor 1, we do have voltage dependent current source, which is GM 1 into VGS 1. So, this is VGS 1 and the VGS is VGS and VDS, they are equal. So, VGS 1 it is here. So, from drain to source we do have RDS 1 or RO 1 along with this voltage dependent current source GMO 1 into VGS, that is the circuit. Now, here we do have the input signal current. So, whenever we are drawing the small signal equivalent circuit, we have to make this is AC ground and this part will be eliminating DC part, but then we have to consider the small signal part. Now, if you analyze this circuit to find what will be the corresponding voltage, which is also equal to VGS 2, we can consider I in, that at this node we can apply KCL. So, I in equals to GM 1 into VGS 1 plus VGS 1 divided by RO 1. So, that gives us the expression of VGS 1 in terms of I in. So, that is equal to I in divided by GM 1 plus 1 by RO 1. And VGS 2 and VGS 1 they are same. So, this is VGS 2 which is also equals to VGS 1 and its expression is given here. So, VGS 2 equals to I in divided by GM 1 plus 1 by RO 1. So, that makes this current GM 2 into VGS 2, it is non-zero, and as a result whenever we will be drawing the small signal equivalent circuit of this entire part. So, we do have the small signal circuit here, small signal equivalent circuit of the application module, and along with that we have to consider this. So, after multiplying with GM 2, this current source which is GM 2 into VGS 2, it is having this expression, namely I in multiplied by GM 1 divided by GM 2 divided by GM 1 plus 1 by RO 1. In fact, this can be well approximated by GM 2 divided by GM 1 by ignoring 1 by RO 1. So, this is GM 2 divided by GM 1 multiplied by I in, and of course, here we do have the application circuit. So, in this case we can say that whatever the current we do have, if it is signal current, so its effect in this application circuit can be considered by considering this voltage dependent current source, which is the input signal here multiplied by GM 2 divided by GM 1. Now, this part depending on the ratio, aspect ratio of these two transistors, it may provide a gain or it may be equal to 1 or it may be sometimes depending on the situation it may be even less than 1. So, that is how we consider the small signal equivalent circuit when the current mirror it is carrying a signal current. So, that is what we say that if the current mirror it is having AC current signal entering into it. So, it is conveying the current to the other side. So, here we can see that this is the input to the current mirror and this is the corresponding output, and its gain we can say that GM2 divided by GM1. So, similar to this MOSFET version, if you consider BJT, there also you will be getting similar kind of expression. Only thing is that here we will be having R pi also. So, let me quickly go into that. Yeah. So, here we do have the circuit. Yeah. So, this is the current mirror, where we do have current is having DC part, along with that we do have the signal current. So, this DC part in the small signal equivalent circuit, that can be removed, but we have to keep this small signal part. So, this I in we have to keep it, sorry, this polarity it should be in this direction, I in, based on this convention. And then we do have the small signal model of Q1, which is having the collector to emitter resistance, which is RO1, and then we do have the GM1 into VB1, and then we do have R pi of transistor 1 along with R pi of transistor 2 in parallel. So, we can directly say that we do have one more resistance, and it produces whatever the voltage here. We may call this is VB1 equals to VB2 incidentally, and that we may also call this is VBE, combined VB1. So, the other side, the small signal equivalent circuit for Q2, we do have voltage dependent current source. So, this is dependent current source. We can say that this is GM2 multiplied by VBE, and then its collector to emitter resistor RO2, and then we do have the small signal equivalent circuit of the application circuit, and then this VCC now it is connected to ground in the small signal equivalent circuit. Now, if you analyze this circuit again similar to the previous case, namely MOSFET based current mirror, you can get the expression of VBE in terms of I in. So, if you consider this I in, and if you equate it to all the current components, which are essentially function of VBE. So, VBE multiplied by GM1 plus 1 by RO 1 plus 1 by R pi 1 in parallel with R pi 2. So, from that you can see that VBE, expression of VBE, VB1 or VB2. So, that is equal to I in divided by GM1 plus 1 by RO 1 divided and plus 1 by R pi 1 in parallel with R pi 2. And this VBE it is same as the VBE of transistor 2. So, as a result this voltage dependent current source it can be written in this form. So, we can see that it becomes, after multiplying with GM2, we do have this current, it is shown here. So, GM2 multiplied by I in divided by GM1 plus 1 by RO1 plus 1 by R pi 1 in parallel with R pi 2. Okay. So, let me rewrite whatever it is given here, it is having multiple mistakes. So, it is GM2 I in divided by GM1 plus R 1 by R O 1 plus 1 by R pi 1 in parallel with R pi 2. So, that is the expression for this current. In fact, similar to the previous case, this part you may ignore. So, in the denominator you do have effectively GM1. So, this equivalent circuit may be written in this form. So, the current source here, dependent current source here, which is I in multiplied by GM2 divided by GM1 in parallel with RO2, and then of course, we do have the application circuits, small signal equivalent circuit of the application module, which is connected to AC ground. So, now we have covered the small signal equivalent circuit of current mirror for different cases, namely if the current mirror is not having any signal current, then it is the equivalent circuit is very straightforward. Whereas, if the current mirror it is having input current, then of course, that current it is coming to the application circuit. Now, let us try to see the application or usage of current mirror in different circuits. So, to start with, let me consider common emitter or common source amplifier. Let me see which one I do have. Yeah, to start with, I do have common emitter amplifier with active load. So, this is the main circuit, where transistor 1 it is working as amplifying device. Input signal we are feeding through the coupling capacitor, and then R1 it is providing a bias current IB. So, this is more like a fixed bias common emitter amplifier. At the collector, instead of connecting a passive load, here we do have Q4, which is working as active load. In fact, we have discussed about the active load circuit considering an independent bias here, but instead of having a bias, this may be better one, particularly if we have say transistors NPN, 2 NPN transistors, they are identical, then what we can do, we can place say R2 here, which is equal to R1, this R1. So, that provides a base current here, which is say IB2, which is equal to IB1, assuming these two transistors they are identical, that provides this current and this current identical. So, I can see this is IC1 and this IC2. IC2 becomes equal to IC1, assuming that transistor 2 and transistor 1 they are identical. Now, by the virtue of this current mirror, and if I assume that this Q3 and Q4 they are identical, then this current IC2 it is getting mirrored here. So, the current flowing through transistor 4, which is also equals to IC2, I should say approximately equal to, because as you may recall that because of the base current loss, there will be a small difference between this current and this current. And if I assume that this is very close to this IC2, and then IC2 and IC1 they are equal, that makes this current and this current are getting matched, which we are looking for. and not only they are matched, both the transistors, transistor 4 and transistor 1 are in active region of operation. Right. Here you might have observed one important changes in the current mirror. If you see this Q3 and Q4, they are forming a current mirror, but type of transistors here we have used it is PNP. So, we do have PNP transistor, we do have a current flow here. In this case, I reference is equal to I C of transistor 2. So, this Q3 and Q4 which are together connected to supply voltage, and then we do have a current mirror getting formed. So, this current mirror, it is very similar to NPN transistor based current mirror. So, whatever the discussion we had before, namely the expression of this current in terms of IS ratio of the two transistors multiplied by this current multiplied by non-ideality factors. One, it is due to the base current loss, another one it is due to early voltage, finite early voltage, that can be considered. So, the expression of IC4 equals to IS4 divided by IS3 multiplied by C2, and then we do have two non-ideality factors coming there. One is due to beta loss or IB current, and other one it is due to the finite value of early voltage. Okay. Now, here as I said that the requirement here it is these two transistors, they are identical. That makes probably many a times it is not so difficult to achieve that, but in integrated circuit, but for discrete component based circuit still there may be an issue of getting two transistors having identical situation. So, I should say theoretically it is fine, but practically you may have to, in case if you want to make this circuit working, you may have to tune this resistor to ensure that these two currents under active region of operation they are equal. Okay. So, once we have these two currents are equal, then to get the gain you can, so the voltage gain which is defined by V out or V output here divided by V in. So, that can be obtained by considering its small signal equivalent circuit. So, if you consider this part small signal equivalent circuit where this capacitor it is working as a short. So, we do have directly V in coming here. So, we do have the V in coming to the base. Let me use different color, otherwise you may get confused here. Yeah. So, we do have V in here, and then we do have R pi, and then we do have so this voltage is VB, incidentally that is equal to V in as we have discussed earlier. So, we do have GM into V in is the voltage dependent current source, and then for transistor 1 its collector to emitter we do have a resistor RO1. On the other hand, for transistor 4 we do have RO4, and we do have supply voltage which is AC ground. Now, the voltage coming here it is the output voltage, and this output voltage, if we analyze this circuit, this output voltage is equal to minus GM1 into V in multiplied by the two resistors in parallel. So, we do have RO1 in parallel with RO4. In fact, so this is the expression, this should be RO4 instead of RO2, it is RO4. So, that is how we can say that we can use the current mirror in common emitter amplifier. So, likewise we can use common emitter current mirror in common source amplifier also. So, in the next slide we do have the corresponding circuit. So, as you can see here, transistor 1, it is working as amplifying circuit. It is having its bias to get a meaningful voltage here. We do have VDD supply, along with that R11 and R12 are forming the potential divider to get VG1. So, likewise here we do have a potential divider consists of R21 and R22 along with the supply voltage to generate a gate voltage VG2. Now, if we consider these two transistors M1 and M2, they are identical, then if this potential divider here and potential divider here, they are identical, providing equal gate voltage, then we can say IDS of transistor 1 equals to IDS of transistor 2. So, we can say this IDS 2 equals to IDS 1, assuming that DC wise this part and this part are identical. And then we do have current mirror formed by M3 and M4. This is a current mirror constructed using PMOS transistor. So, here we are assuming that M3 and M4 are identical. So, if they are identical, then whatever the current it is flowing, namely IDS 2, it is nicely getting mirrored here. So, we can say that ISD 4 equals to IDS 2, or to be more precise, it is having a ratio, aspect ratio relationship. So, we consider W4 by L4 divided by W3 by L3, then multiplied by whatever non-ideality factor, and if I assume that this is equal to 1, which means that transistor 3 and transistor 4, they are identical, that makes ISD 4 equals to IDS 2, and then at the lower side we do have transistor 1, which is having IDS 1. So, that makes the current here it is equal to this one, assuming this IDS 2 equals to IDS 1. So, with this assumption, it may not be very difficult to match the current of the amplifying device and the active load device, and many a times in integrated circuit, particularly integrated circuit, matching getting the matched characteristic of two transistors, it is not so difficult, and this circuit it is hence quite frequently used in integrated circuit. After getting the DC operating point correct, we can probably try to get the gain of the circuit, and the gain it is defined by the voltage coming here, V output divided by V in. So, to get the relationship between this output signal and input signal, we can draw the small signal equivalent circuit. So, here we do have the small signal equivalent circuit. Let me clear the board and yeah. So, yeah, some part of the small signal equivalent circuit is missing. So, let me draw that part, particularly this part. We do have the input directly coming here to the gate node of transistor 1, and that produces VGS 1, and incidentally this VGS 1 equals to V in. So, we can see that voltage dependent current source, it is GM 1 into V in, and at the output side we do have this RDS 1, which we are denoting now by RO 1. So, we do have RO 1. Likewise, we do have RDS 4, which we are denoting by RO 4. So, we do have RO 4, and this is of course, it is AC ground, and the output signal it is coming at this node. Now, analyzing this circuit, what we can get it is V output equals to the current flow with a minus sign, of course, with this convention of this current direction. So, this is GM 1 into V in multiplied by RO 1 in parallel with RO 4, and yeah. So, I should say, yeah, I should have multiplied by V in. So, that gives us the voltage gain AV equals to V output divided by V in equals to minus GM 1 RO 1 in parallel with RO 4, right. So, likewise, this current mirror it is also having application in differential amplifier. So, this usage of current mirror is also there in differential amplifier, and in differential amplifier the current mirror not only it can be used as biasing element, but also it is used as current carrying element. So, the discussion there it will be quite involved. So, we will be discussing that, but let me take a break, and then we will be talking about usage of current mirror in differential amplifier. So, we will be coming back after the break. Thank you.